Hello everyone, welcome back. This is chapter number 4. Opamp and its applications. In the last session, we had seen what is Opamp, direct coupled high gain differential amplifier, and I explained what is differential amplifier and how to get direct coupling. Means we don't want input capacitor, we don't want output capacitor, we don't want bypass capacitor, right? We used dual power supply and a differential amplifier configuration with the current source or resistor in the bottom. Then it gave us direct coupling amplification. Now, I want to explain one more point. Means let us say with respect to the block diagram, right? I can say op-amp compensation. The topic is op-amp compensation. Op-amp compensation. You'll understand the meaning of compensation, okay? And in the last class, if you see the block diagram of op-amp, I'm not explaining like completely. The first stage is Darlington pair. This is nothing but Darlington pair. This is Darlington pair. Right? And this is Darlington pair. Because we have two inputs. This is Darlington pair. Now this is differential amplifier. And actually there is something called differential output to signal output conversion using current mirror, which I did not explain. And this is what is your CE amplifier. This is also CE amplifier, but differential input and the signal output, okay? And now the last one, level shifter or buffer amplifier. This is buffer amplifier, which is basically CC amplifier. This is nothing but CC amplifier. And this is what your output V0, right? And this is nothing but V1 and this is V2. Now tell me how many stages are there from input to output? Can I say 1, 2, 3, 4? We have 4 stages, okay? Then if you say this is what is your open loop op amp, let us say this is what is your open loop op amp, right? This is what your open loop op amp, and equivalently people represent it like this. This is what your op amp symbol, this is V0 and this is V1, this is V2, right? Let us say minus and plus. What is the meaning of minus and plus? Now when input is increasing here, your output will decrease. When input is increasing at V2, your output will increase, because by default if you don't specify any direction, what does it mean? Positive direction. When I say 2, by default plus 2. If it is negative, we have to say minus 2. We have to explicitly specify the negative, but no need to specify the positive sign, because default that is positive. Similarly, this is positive. What does it mean? The phase difference between V2 to V0 is 0 degrees. Or what does it mean? When V2 increases, V0 increases. When V2 decreases, V0 decreases. Same phase. Now coming to V1, right? When V1 increases, V0 decreases. When V1 decreases, V0 increases. Therefore opposite phase. That's why this is called inverting terminal, because there is inversion between V1 to V0 and this is non-inverting terminal because it is not inverting your V2 to V0. Therefore, whatever V2 direction you have, the same direction you can get at the output. Therefore, this is non-inverting terminal. When I say, and this is what is defined with what? This is what is defined with differential gain AD. But we have something called common mode gain, which we don't want. We want common mode gain to be 0. But practically we will not get common mode gain 0 because of differential amplifier, the bottom practical current source are resistor. Okay, what it may be. Then what is V0? V0 is equal to AD into V2 minus V1. Therefore, V2 minus V1. Because plus plus. Therefore, V2 minus V1 into AD is nothing but your V0. Therefore, this is what people say AD into VD. VD is nothing but the differential input voltage. Right? This is what the symbol people specify for your op-amp. And we had studied what is Darlington pair. Basically, two-stage CC amplifier, differential amplifier, common emitter amplifier, CC amplifier or buffer amplifier. Strictly speaking, with respect to if you take a configuration as a stage, then 2 CC amplifiers, 2 stages, 1 more stage, 3, 4, 5. We have total 5 stages from input to output. You may say, I want to improve voltage gain further. Now let us say this is what is having voltage gain of 400, this is having voltage gain of 500, 400 into 500, 2 lakhs, 2 into 10 to the power of 5. Even if that gain is not enough, what to do? You put one more CC amplifier, then your gain will be this gain into this gain into this gain. But you will not get any gain from Darlington pair and then CC amplifier. Why? What is voltage gain of Darlington pair? That is 1. Because this is CC amplifier, therefore the voltage gain is approximately equal to 1. Here also the voltage gain is approximately equal to 1. Then what is voltage gain of differential amplifier? Let us say that is what is gain AV1, voltage gain of C amplifier AV2, and voltage gain of buffer amplifier, this is approximately equal to 1. Overall, what is your voltage gain? AV1 into AV2. These two are your main amplifiers or multi-stage amplification. Therefore, we are getting huge gain, that is fine. But if you want to increase your gain further, what you may think, let us add one more stage, right? If you add one more stage, AV1 into AV2 into AV3, you will get gain in the order of tens of lakhs or in the order of crores also. Therefore, can you add the number of stages whatever you want like that? From circuit perspective, yes, you can add. From circuit perspective, like I want huge gain. If I want huge gain, 400 into 500 into something, therefore you will get more than 2 lakhs. But remember, if you think from system perspective, because we are going to use this op-amp, we are not going to use this op-amp in open loop condition, or we are not going to use this op-amp always in open loop condition. We are going to use op-amp in feedback. That is what? Op-amp applications, right? When you use op-amp in the feedback, right, then it will become closed loop system. Then it will become closed loop system. Then when it is becoming closed loop system, then the closed loop system should be stable. The closed loop system should be stable. That depends on your open loop number of poles, right? Now if I go to a little bit about the control systems concept, right? If you consider any closed loop system, this is what is open loop op-amp, right? This is what people say open loop op-amp. This is open loop op-amp. But if you take a control system, right, then maybe you take this once again and then represent like that. Then I'll explain something called stability of a closed loop system. Then I'll come back to op-amp. Then let's see what to do to improve the stability of your system when it is configured into closed loop system. That part I'll explain. First of all, take it. Then we will see the closed loop system stability. You have written this already. Therefore, if you ask me the overall gain AD, right? Therefore, AD is equal to AV1 into AV2. If you take IC 741 op-amp, it will be in the order of 2 into 10 to the power of 5. This is for IC 741 op amp. Which is basically 106 dB. Considering the gain by Darlington pair 1, the gain by buffer amplifier 1. Then I'll explain, before going to the closed loop system, I'll explain something called Miller's theorem that is required for us to get it. Therefore, let us apply Miller's theorem. Actually, I don't want to rub it because I'm going to come back to this, because we are going to do something that is nothing but op-amp compensation to get stability from closed loop system if you use op-amp as open loop system. Hope this is done, right? Now, what I do, anyway, I'll come back to this. The limitation, what is the limitation? Because of the board, what it may be. I'll come back and then I'll add something or I'll modify this, okay? But this is under op-amp compensation only, okay? Now, write down Miller's theorem. Right? What is Miller's theorem? If you have any system, open loop system, having some gain A, then let us say this is what is V0 and this is Vi. Right? Now, and if there is a feedback between output to input, let us say it is some Z. Okay? Then what is A? A is nothing but A is equal to V0 by Vi. Okay? This is what is our system. If this is what is our system, now according to Miller's theorem, we can resolve the feedback impedance between output to input, right, equivalently only at input. Let me call this as Z1, and equivalently only at the output. Let me call this as Z2. Therefore, equivalently we can represent these two like this. Means if there is a feedback component between output to input, that we can resolve into the feedback component exactly at input, feedback component, the component of feedback at output. Then what is Z1, what is Z2? Okay. If you have like this, wherever you have some impedance in between output to input, we can apply Miller's theorem and then we can solve it. Okay. Therefore, A is nothing but V0 divided by Vi. Now, I can derive quickly what is Z1 and then what is Z2, right? To find Z1, right? Now, the first one, to find Z1. To find Z1. Okay. Therefore, now if I take only input part, this is nothing but your amplifier A. Now, this is nothing but your Z1, right? And now this is what is your Vi. Let us say, if you say that both are equal, when can you say both are equal? If KCL, KVL, the equations are not disturbed, means the voltage drop across the element, or the current which is what is flowing through the element, or current which is flowing through a node, KCL is not disturbed, KVL is not disturbed. Until unless you don't disturb KCL and KVL, we can modify the circuit in any way, right? Therefore, this is kind of modification, but we should not disturb KCL and KVL. Okay? Tell me what is KVL? KVL means what is voltage at the input with respect to ground. Always when you specify a node voltage, reference is always ground. What is the voltage at this point with respect to ground? Vi. Tell me here, by having the component of Z at the input, then what is the voltage at this point with respect to ground? Vi. It's not changed. Therefore, KVL, our voltage is satisfied. Now let's see KCL. What is KCL? Let us say this is what your Vi, right? Which is what is giving some current I1. The input is having some current I1. Let us say this is what is having I1. Similarly, here also, if input current is also I1, here also, here I1, then both are same. Therefore, according to KCL, if you have the original circuit is this, then the current which is coming from Vi is I1. If the same current is also coming from Vi, I1, good. And out of I1, let us see the current which is what is entering into your amplifier is I2. Then the current which is what is entering into the next branch, let us say this is I3. If the same current is flowing out of I1, let us say the current which is what is entering into amplifier should be I2. Then only I will call that both are same. And the current which is what is leaving from this node, which is the branch, but wherever it is going doesn't matter. The KCL, according to KCL, I1 is equal to I2 plus I3. Therefore, I1 is equal to I2 plus, it should be I3. If this is what is the scenario where KVL is satisfied, voltage is not disturbed and current is also not disturbed, then only from input side or at a node, whatever node we have here with respect to that node point, both are equal. Then tell me what is I3, equate both of them, you will get the answer, right? That is what it is. Therefore, this is nothing but what? The same thing whatever I explained there, the same thing here, right? Therefore, here this is nothing but what? I1. When I say this is what your I1, actually that is represented there, then what we can do, the same thing I'll use. Therefore, tell me at input side, okay? At input node, right? Tell me what is I2, according to this, what is I2? I3 is equal to what? This voltage minus this voltage divided by Z, which is Vi minus V0 divided by Z. Okay? This is I3. Now, the equivalent using Miller's theorem, right? What is I3? Using Miller's theorem, what is our I3? I3 is equal to Vi minus 0 by Z1. Vi minus 0 by Z1. Both are same or not? Yes, both are same. Therefore, this is equation 1, this is equation 2. 1 is equal to 2. 1 is equal to 2. Then what is this? Vi minus V naught divided by Z is equal to Vi divided by Z1. Take this Z1 to left hand side and then this to right hand side. Okay, then you'll get it. Or I can say, because your aim is to find Z1, therefore what is Z1? Z1 if you take, then what you get? Z1 is equal to this Z into Vi divided by Vi minus V naught. Can I divide by Vi both numerator and denominator? Yes. If I divided that, then Z into Vi means divided by Z divided by Vi 1 minus V naught divided by Vi. What is V naught divided by Vi? That is nothing but your A, open loop gain, right? Therefore, what is Z1? Therefore, Z1 is equal to Z divided by 1 minus A. This is Z1. See, this is based on network analysis. This is what is given by Miller. That's why this is what is called Miller's theorem. Miller proposed or Miller derived this and then equivalently told that this is what you can equivalently represent. Then what is Z1? Z1 is nothing but Z divided by 1 minus A. In the same way, we need to find Z2 with respect to the Z and all, right? How will you do that? Just to do that, what I do, this is nothing but your V naught. This is your V naught, right? This is V naught. Now to make both of them equal, right? This is at input node. Now let me use different color. Let us say this is what is giving some current. The current which is what is entering into your V naught, because I1, I2, I3 all are used. Then I can say this is what is some I1 star. Okay. Then what is the current? Let us say the current which is entering into your op-amp, right? Sorry, amplifier. Let me say this is I2 star. Then let us say the current which is entering here I3 star. Okay. Now the same current, if KVL is satisfied, if the same current is entering, let us say this is I1 star and the current which is entering into your amplifier, if that is I2 star, and the current which is entering into Z2, if that is what is I3 star, the current which is leaving from this node, then I can say both are same, right? Therefore now to find Z2, now case 2, to find Z2. Okay, I'll explain. Before that you try to get Z1. Write down After this, you try to find Z2 on your own. Similar way, you find what is I3 star V0 minus VI divided by Z. What is I3 star V0 minus 0 by Z2. Equate both of them, then find Z2 with respect to Z, you will get the answer. Okay? Same way. Done? Okay. Now Z2. Tell me what is I3 star? I3 star is equal to V0 minus Vi divided by Z. And what is I3 star? From this Miller, I3 star is equal to V0 minus 0 by Z2. V0 by Z2. Both are same, right? When both are same, then therefore both are equal. Right? Then V0 minus Vi divided by Z is equal to V0 by Z2. If I take this, then Z2 is equal to Z into V0 divided by V0 minus Vi divided by V0. Then Z divided by 1 minus Vi divided by V0. That what is Vi divided by V0? V0 by Vi is nothing but A. Then this is nothing but 1 minus 1 by A. This is what is Z2. Okay. If A is very much greater than 1, Z2 is nothing but Z. Right? If A is very much greater than 1, then Z2 is nothing but Z only. It's not changing. Therefore, whatever feedback impedance you have, that is what is coming as it is at the output. You can represent as it is at the output if open loop gain is very much greater than 1. This is what I am going to use later, Miller's theorem. The Z can be resistor, Z can be capacitor, Z can be inductor, or Z can be combination of R, L and C. Could be anything, but if you represent it as Z, how to resolve that feedback resistor Z from the feedback component 2 at the input side as well as output side. I'll give you 30 more seconds to complete. Then after that I'll explain something called stable system or unstable system or the reasons to get stability. Then I'll apply to Opamp. Then with that Opamp block diagram or Opamp portion is over, then we can go directly to applications. Okay. Applications are interesting because each circuit is an example. Even though we are solving problems, each problem is an application of Opamp. But few problems to familiarize the theory and familiarize the procedure what we need to apply to solve the problems. Over? Okay. Now let me erase this. Now, let me ask, tell me, is one pole system always stable? When I speak about one pole system, one pole of what? One pole of open loop system. Because if you consider unity gain feedback system, let us consider unity gain feedback system, unity gain. Why we consider unity gain feedback system? I will explain from oscillators, okay? Unity gain feedback system, always if you take control systems, right? Everywhere people consider unity gain feedback system only. If it is not having unity gain, convert into unity gain feedback system. Why to convert into unity gain feedback system? Give me some time. I'll explain part of Opamp applications, that is nothing but sinusoidal oscillators. Okay, there I'll explain unity gain feedback system. What is it? Let us say this is what your G of S, right? And let me take negative feedback and unity gain feedback. Okay, and this is what is input and this is what is output. Therefore, let us say this is what is y of t and this is what is x of t. Right? Now tell me, for unity gain feedback system, now tell me what is your transfer function, because everything in S domain, let me represent in X domain. Therefore, this is x of s and then y of s. According to control systems, this is what is R of s and then this is C of s. This is R of s and this is C of s. Okay. Then what is your closed loop transfer function? And closed loop transfer function is equal to G of s divided by 1 plus G of s into H of s. H of s is 1. Therefore, this is what? Remember, whatever root locus, polar plot, Bode plot, Nyquist plot, or MN circles, what are all the techniques we are using in control systems to find the system stability? Remember, those are all techniques valid only for unity gain feedback system. Only for unity gain feedback system. That is the reason why, because the feedback is always unity. Therefore, let us consider open loop system. What is open loop system? G of s. Therefore, this is nothing but your open loop system. This is open loop system. Open loop system. Now, when I say open loop system, right? But practically, you may not have always unity gain feedback. But we are analyzing the techniques only for unity gain feedback. Then, how to do or what to do? If you speak about only systems of stability, right? Then I don't bother about what is my exact output. Is it my exact output or is it my exact output or internal to the G of S is my output? Doesn't matter, because if a system is stable at every node you consider in the system where the system is stable, all the signals at every node are bounded. All the signals are every node bounded. If that is the scenario, then practically you may not have always unity gain feedback. Then what to do? Then let us say if you have H of S, right? If you take, but practically the system could be with H of S. Then therefore this is what is our G of S. Then this is what is positive, negative unity gain feedback. No, now it is not having unity gain feedback. Now this is having H of S. Now this is H of S. Okay, now this is R of S, C of S. Now tell me for this, what is the closed loop system? G of S divided by 1 plus G of S into H of S. You know that. But it should be converted into, we can convert, therefore we can convert above control system, we can convert above control system with unity gain feedback. How? Therefore, if you see here, can I write this G of S? in here, then can I write it like this? This is G of S and now this is H of S, right? Now treating this as the new open loop system, I can say this is G dash of S, let us say. Now this is plus minus, okay, this is the input. Now you can treat this as unity gain feedback. And now this is what is our input and this is what is the input, okay. Actually this is what is the output with respect to this. This is what your C of S, right? Then what is this? This is what is the quantity, right? Now that is what is your output. Here we are treating this output because my worry is when you say this is what is new output, let us say this is what your feedback quantity, this is Vf of S, then this is nothing but Vf of S, then this is what your R of S. Now I am speaking about system stability. If I speak about system stability, then this is nothing but unity gain feedback system. Then once you know the system stability with respect to this, then can't you find C of S? If you know Vf of S, right, divided by H of S, you will get C of S. Finding output, let us say this is what your output, finding output from this is also easier. But here my intention is not to say what is my output. Sometimes, first of all, I want system stability. For system stability, I can convert the system with feedback H of S into unity gain feedback, combining G of S into H of S. Actually, this is what is called loop gain. People always try to get loop gain. Maybe to make it easier, ultimately, therefore, what is this now? Therefore, equivalently, if I say this is nothing but your new open loop system G dash of S and converted into unity gain feedback, right? And now this is what is your equivalently. Therefore, now this is what is, if you say this is your output, right? This is what is your input, but your actual output is internal to your open loop system. Doesn't matter. First of all, I want to analyze the system stability. Once you know the system is stable, then whatever output you want, we can calculate. That is simply mathematical analysis. But for system stability, you can manipulate everywhere, because if a node is stable and if a node is bounded, this is also bounded. If this is bounded, this is also bounded, right? Therefore, if you know the system is stable with respect to this, then done. Therefore, any system can be converted into unity gain feedback system, and this is what it is, open loop system, and people call this as loop gain. This is what is called as loop gain. Therefore, what is loop gain? G of S only. Here, what is loop gain? G of S into H of S. Therefore, what is loop gain? G of S into H of S, which is G dash of S. What is loop gain? G dash of into. Therefore, now this is what is our open loop system. This is what is our open loop system. This is what is loop gain. Okay, take it. Therefore, ultimately, whatever loop gain you have, that is what is important. If you consider loop gain as your open loop system, then it is automatically unity gain feedback system, right? That's why loop gain is very important. Therefore, to make loop gain as open loop system, this is unity gain feedback system. Now this is what your loop gain. This should be represented as loop gain. Therefore, the loop gain is completely represented with open loop system, and then people speak about stability of that system is unity gain feedback system. I'll give you 30 more seconds to complete. Then when I speak about one pole system, I'm speaking about loop gain transfer function poles. I'm just again notifying a point saying that when people say is one pole system stable, two pole system stable, three pole system stable, that is depending on loop gain number of poles. Therefore, if you make it like loop gain with open loop system, then this is with unity gain feedback system. When I say one pole of this. When I say two poles of this. Let me give you one example. Let us say originally this is what your system, then let us say this is having one pole and H of S is having one pole. Then don't say that this is one pole system, because according to control systems we always take the open loop system's pole but considering unity gain feedback. But here it is not having unity gain feedback, right? But the G of S, original G of S is one pole, H of S is one pole. Then if you want to apply control systems technique, convert into, therefore what is loop gain number of poles? Therefore loop gain number of poles, one pole, two pole. Now that is two pole system. Therefore two pole system. Then is two pole system always stable? Because when you speak about one pole system, two pole system, three pole system, therefore the number of poles what you are speaking, right? That is for loop gain number of poles with unity gain feedback. That is very important point. Once this is clear, you can apply these techniques, or we can take the techniques, we can adopt the techniques from control systems. Okay, that's what I want to say. Because let us say this is what your op-amp, but in the feedback you can have a pole, right? Then even though op-amp is stable, but when you have a pole, one more pole in the feedback, overall it may not be stable. You understand the point? Therefore overall system should be stable with respect to closed loop functionality. Okay, fine. Therefore let me erase. Now let me ask with respect to open loop system or loop gain number of poles. When I say one pole, that G of S one pole. When I say two pole, that loop gain two poles. Three poles means loop gain three poles, like that. But having unity gain feedback are converted into unity gain feedback. I hope this is clear. Therefore the terminology is clear. Now let me ask you, we can use either root locus or Routh-Hurwitz criteria, Bode plot, Nyquist plot, polar plot. There are so many techniques to find or to comment on system stability. Okay, now tell me one pole system. Is one pole system always stable? If you take root locus, let us say we have one pole of loop gain, remember, okay, which is what we are considering closed loop transfer function and having unity gain feedback, then G of S one pole. Then fine, then tell me what is your root locus. Means if you take G of S, right, let us say K by S plus A. Therefore what is the pole here? This is what is the pole. This is what is minus A. This is what your pole, or maybe if you want you can say this is what is pole S plus P1. Therefore this is what is minus P1, right? This is what your pole. Therefore typical, the convention what people follow is S plus A and all. That is fine. Okay. Now, if that is the scenario, this is what is S plus A. Then this is minus A. Now, when K is varying from minimum to maximum, then how the closed loop system's poles, right? The closed loop system poles should be always located in the left half of the S plane. When you draw the root locus, always the closed loop system's pole, when K is varying from minimum to maximum, then all the poles are located in the left half of the S plane. Therefore, I can say system is always stable. System is always stable. System is always stable. What does it mean? Two-pole system is always stable. Can I say that? Take it. The time is over for the session. Then after taking this, then what I want to tell, let me tell you. We will consider two-pole system, three-pole system or four-pole system. Enough. I want to comment on the system is always stable for how many number of poles, right? Then, therefore, we cannot take the number of stages whatever you want from your circuit, right? That is what I am going to correlate from system stability. Okay? Take it. I will continue in the next session. Thank you. You can take it.